Hello everyone and welcome to week 8 TA session for biointerface engineering. So in this session we'll discuss all the topics that were covered in week 8 and then we'll solve the assignment problems for week 8. So there were 3 lectures covered in week 8, lecture 22, lecture 23 and lecture 24. Lecture 22 covers about surface characterization. The surface characterization can be broadly classified into microscopic and spectroscopic techniques. So the microscopic techniques include optical microscope, includes the optical microscope, the electron microscope, scanning probes, scanning probes, field emissions, and low energy electron diffraction. And then in detail different microscopic techniques were discussed. First, for the optical microscope, um, basically these are low resolution as compared to other microscopic techniques, and the resolution power of an optical microscope can be given by x equals to 0.61 lambda, 0.61 lambda by n sine alpha. N sine alpha, where lambda is the wavelength of light and n is the refractive index of the medium. Then we went on to then the different electron microscopy were discussed, such as scanning electron microscope, wherein uh, high energy electrons are bombarded onto the surface, and based on the emitted electrons, that could be either X-rays, backscattered electrons, secondary electrons, or Auger electrons. Based on this emission electrons, the images can be analyzed. Then similar to SEM, there is one more electron microscopy technique called as TEM, which is transmission electron microscope. And instead of um, reflection, the electrons are basically transmitted through the samples, and then the transmitted electrons can be analyzed to form light or dark field images. And then we discuss about scanning probes. Scanning probes are there are two types of microscopes that uses the scanning probe principle, the STM, or the also called as scanning tunneling microscope, and AFM, or atomic force microscope. Both of these have small detector tip which scans over a surface, and this detector in STM basically exponential decay in the tunneling current between the tip and the surface. uh, Conducting surface is gives an information about the surface, and in atomic force microscope, uh, close interaction between the tip and the surface leads to attractive and repulsive forces, and the deflection in this deflection of the tip leads to an determination of the surface. Then we went on to discuss the X-ray, the diffraction techniques, wherein XRD was discussed, or X-ray diffraction technique. It is another imaging technique wherein there is an and incident light, and then it is diffracted, and based on the angle formed here, which is 2 theta, there is a equation established to lambda equals to 2d sine theta, 2d sine theta. So lambda is the incident wavelength of the incident light, theta is the angle formed after diffraction, and d is the interplanar spacing. So this has high resolution, gives information about the interplanar spacing. And these microscopic techniques can be used for surface characterization to analyze the surface chemistries after modification, or even before modification, to see changes in the uh, to analyze the surfaces and what all changes has occurred on the surfaces. And with different kinds of macroscopic techniques, based on we can based on the information we want, we can use different kind of microscopic techniques with better resolutions. And then spectroscopic techniques were discussed. Here basically two different techniques were covered. One is FTIR. We have already discussed about FTIR, where based on the absorbance of the infrared light, uh, the molecules undergo rotational, vibrational, and other modes, and they produce specific peak, different structures such as alpha helix, beta sheets. They produce different peaks based on this absorbance of infrared radiations, and these peaks give information about the secondary structures. Then another microscopic technique was discussed, which is Raman spectroscopy. So Raman spectroscopy basically uses a monochromatic laser to analyze rotational, vibrational, and other modes of molecules in a system. So there is an incident laser light that illuminates the sample, and then based on the radiation. Based on this incident lights, the molecules are excited to a higher state of energy level and then they relax to a vibrational state. And this vibrational excited state gets information about is the Stokes-Raman scattering, and analyzing these states gives information about the molecules. So similar to FTIR, here also the different secondary structures have uh, spec different peaks for different structures at specific wavelengths. Uh, so in the next lecture, that is lecture 23, it covers about self-assembled monolayers, also called as SAMs. So briefly, the history of SAMs was discussed, uh, and how it started and why we are studying about it. So the self-assembled monolayers are basically they have the ability to assemble themselves uh, in monolayers over a surface, and they are highly oriented, ordered 2D structure, 2D molecular arrangement over the surface. They are covalently linked to the surface, and they can be altered. These coatings can be altered based on specific functions. So these self-assembled monolayers has a typical structure. It has one ligand and then a spacer and then a terminal functional group. So based on the surface we want to modify, we can change the ligand or the terminal surface. We can change the ligand, and based on the interaction we want of the surface with the host, we can change the terminal group. So this is basically a functional group, and this is a alkane chain spacer, and these ligands bind to the surface by covalent bonding. And then we discuss about the kinetics of SAM formation, and uh, followed by the factors affecting SAM. For example, water. In the absence of water, there will be incomplete attachment, but in presence of excess of water, it will be polysilane bond formation in the solution. Uh, so we need appropriate amount of water. So this is basically a chemical reaction wherein the ligand is interacting with the surface to form a covalent bond. So we want the water, temperature, concentration, reaction time, everything to be appropriate, and any changes in this parameters will lead to change in the interaction or bonding of this these molecules over the surface, and won't give us the desired coating over the surface. And then the kinetics of attachment was discussed. This was followed by so in the kinetics of SAM formation, the a specific case we can take, such as the surface silica surface. When it is incubated within the saline solution, it will first lead to attachment. That is, will lead to attachment of these uh, silane molecules in over the surface, and then over time it will undergo reorientation and it will arrange themselves into a monolayer. Rearrangement. And then after coating, then it can be characterized. A specific case was taken where it was coated with the saline solution, and then it was characterized by FTIR, wettability in the contact angle, and atomic force microscopy to check the surface modification. And then the effect of modification on the interface properties was also discussed. Then in the next lecture, that is the last lecture, lecture 24, surface functionalization of titania implant via the self-assembled molecules, SAMs, where for increased protein adsorption and fibroblast adhesion was discussed. So basically in this lecture a specific case was taken wherein the titania implant, usually used for bone tissue engineering, which is well established, and this implant was then functionalized by SAMs, and then the different techniques were used to analyze the protein adsorption over it and cell adhesion. Cell cytotoxicity, cell adhesion increase or decrease in the fibroblast adhesion, surface area available for adhesion. All those things were discussed after functionalization. So these were all the topics that were covered in this week. And now we'll discuss the assignment problems that were based on these topics. So let's see the assignment questions. Here is the first question for the assignment. Which of the following microscopy techniques has the highest resolution? The options are electron microscopy, scanning probe microscopy, field emission microscopy, low energy electron diffraction. So the correct answer here would be low energy electron diffraction. So this basically uses X-ray and it gives information between the interplanar spacing of the atomic arrangements. So this has the highest resolution as compared to electron microscopy or scanning probe microscopy or field emission microscopy. Okay, so here is the next question. What is the relation between the resolution power of an optical microscope and the refractive index of a medium? The options are directly proportional, inversely proportional, exponential proportional, or not related. Okay, so the resolution power of an optical microscope, the resolution power is given by this equation 0.61 lambda by n sine alpha. So here lambda is the wavelength of the light and n is the refractive index of the medium. So you can clearly say the resolution power is inversely proportional to the refractive index. So second option will be the correct answer, inversely proportional. Okay, so here is the next question. Which of the following microscopes can be used to visualize the 3D structure, 3D interior structure of biological samples? Electron microscope, scanning probe microscope, field emission microscope, or confocal microscope? Which of the following microscopes can be used to visualize the 3D interior structure of biological samples? The correct answer here would be confocal microscope. All the other gives more detailed or high resolution of the interior structure of the biological samples, whereas the confocal microscope will give us just the right information about the 3D interior structure. Here is the next question. Which of the following types of electron emission are used in the scanning electron microscope to analyze the surface morphology? Options are A, backscattered electrons, B, secondary electrons, C, auger electrons. The options are A and B only, A and C only, A, B and C, or C only. Which types of electron emission are used in scanning electron microscope? So the correct answer here would be A, B and C. So all these electrons, backscattered electrons, secondary electrons, and auger electrons are used in the scaling electron microscope to analyze the surface morphology. Here is the next question. The change in the binding energy of a core electron of an element due to alteration in its chemical bonding is referred to as. Options are energy shift, chemical shift, valency shift, or structural shift. And the correct answer here would be chemical shift. So in only chemical shift, the change in the binding energy of a core electron of an element happens due to alteration in its chemical bonding. Okay, so here is the next question. In the self-assembled monolayers, what is the function of the spacer? Options are chain and surface interaction, providing functional groups, offering thickness to the monolayer, or protection of the functional groups. So here the correct answer would be option C, offering thickness to the monolayer. So the function, so basically this, if this is the surface, then in self-assembled monolayers, first there is a ligand that has covalent bonding with the surface, and then there is a spacer, which is basically a alkane chain, and then we have the terminal functional group. So different kind of these spacers provide a thickness to the monolayer. Here's the next question. For the surface modifications, the thiol group can be used over which of these surfaces? The options are gold surface, silver surface, copper surface, or all of these. The correct answer here would be all of these. So gold, silver and copper, all of these react with the thiol groups, the SH groups. So all of these surfaces, for modifying all of these surfaces, we can use the thiol groups as ligands that can bind with these surfaces. This can be a thiol group. And then we can have the spacer molecules and the terminal functional group. So we can modify the surface of gold, silver and copper using these thiol ligands and form self-assembled monolayers over these surfaces and modify them with desired functional groups for application of and application of interest. Okay, now here is the next question. Which of the following is not a feature of titanium and alloys? The options are low elastic strength, good fatigue strength, low osteoconductivity, and high osseointegration. Which of these options is not a feature of titanium and alloys? So the correct answer here would be osseointegration. So osseointegration, basically titanium and alloys are used for bone tissue engineering. And osseointegration is these bone cells or osteoblasts integrating with the implants or adhering and attaching over the implants to form it a part of the body. So the titanium and alloys, these are highly inert materials and they don't really interact with the cells. They don't have high osseointegration, which is why we discuss in the lectures about several techniques of coating the titania and alloys, the titanium implants such as the TI6 AL4B and coated with different calcium phosphates, hydroxyapatite, TCP, tricalcium phosphates, and the biphasic phosphates, mixture of both HA and TCP. And we coat them over these titanium plants and study their effect on cell adhesion, protein absorption, and all those things. So they don't have high osseointegration. So the correct answer would be option 4. And now we have a numerical question. So the question is, a mixed surface of A and B is designed with the water contact angle of 77 degrees. The water contact angle on A and B are 100 degrees and 60 degrees respectively. Estimate the fraction of A in the mixed surface. Options are 0.4, 0.58, 0.43 or 0.7. Okay, so now we'll try to solve this equation. So first of all, the fraction, different fractions on a mixed surface. If fraction A plus fraction B, these two fractions equate to 1. This will be our equation 1. And then using these angles, we can form a second equation. So we'll use the equation cos theta equals to FA cos theta plus FB cos theta. Now the angle of these angles are given. The first one is 77 degrees. So this would be cos 77 degrees equals to the water contact angle on A is 100 degrees. So this is FA cos 100 cos 100 plus FB for water contact angle of B is given as 60 degrees. So this will be FA cos 60 degrees. Now writing their values, we will get cos 77 is equivalent to 0.2249. Then we have FA cos 100 is minus 0.17. So okay, it's 0.17 plus cos 60 is 0.5. So this will give us FB 0.5. So this will be our second equation. Now we'll try to solve these two equations. So if we just multiply this first equation with 0.5, we'll be able to equate them. So that will give us 0.5 equals to FA into 0.5 plus FB into 0.5. This is our equation 1. which is multiplied overall by 0.5. So now these two are equal, so we can simply subtract this to eliminate the FB value. Then this will also get subtracted, and this one as well. So this will give us, this is 0, and minus 0.17 plus minus 0.5 will give us minus 0.67 FA, and then we have here 0.2249 minus 0.5, which will equal to point minus of 0.2751. 2751. So we can get the value of FA, which is equal to 0.2751 by 0.67, so it will be 0.41. And FB will be basically 1 minus 0.41, which is equals to 0.59. So the question asks about the fraction of A in the mixed surface. So fraction of A or FA is zero point 0.1. So first option 0.4 is the closest one, and that will be the correct answer. Here is the next question. For a copper potassium alpha based XRD measurement, calculate the D spacing in angstrom of a material at an incidence angle of 60 degrees. The options are 0.53, 0.55, 0.66, and 0.88. The correct answer is already given here, 0.88. So we'll now simply try to solve this equation and get the answer. So for XRD measurement, the equation that is used is n lambda equals to 2d sine theta, 2d sine theta, and here n is just an integer, so we'll consider this as 1, and then lambda for this, the lambda is fixed, that is 1.54 angstrom. And then we have 2d sine theta, d, and we have the incidence angle 60 degree, so it will be sine 60 degrees, sine 60, and then so we'll get the d will be exactly 1.54 divided by 2 and sine 60 degree. Sine 60 degree is basically 0.866. Now if you divide this or if you solve this, you'll get 0.88, which is our solution. So the fourth option, 0.88, will be the correct answer. Okay, so these were all the questions and for this week, and this was the last lecture. So we have covered, so in this 8 weeks we learned about different surface modifications, host cell response, bio implants, different surface analyzing techniques. Learned a lot of things, and I hope this was useful. These TA sessions were useful for solving the assignments. Wish you all the best for your exams. Thank you.